Hey, what's going on? It's your old pal, Mr. Cook. We just finished up 16 and 17 and 18. Now we're going to make a video going over 19 and 20, I suppose. Yeah, okay. So it's more about area. What we talked about in the previous video is, if you need to find the area of a polar curve, it's always the same formula. Area is equal to the integral between two radial bound or angular bounds. And then it's going to be 1/2 of the polar equation squared, and then d theta. Okay, the area between the polar curves are, hey, wait a minute, those are the same ones, aren't they? As the previous problem? They are. Okay, cool. So we already graphed this out. So just use your calculator, graph it out. Here's how it looked. Oops. Out by 3. And let me make the graph a little bit larger just in case we need to explore it a little bit. All right, so 1, 2, 3, 1, 2, 3. All right, so here's our little circle. R equals 3. 0 degrees, 90 degrees, 180 degrees, 270, and 360. There we go. Okay, and then we got our cardioid here at 0 degrees for sine. That'd be 0, so it'll be out to 5, 1, 2, 3, 4, 5. And then same thing over here, 5 in this direction. And if it's 90 degrees, then that's 1. So 5 plus 4 is 9, 3, 6, or 4, 5, 6, 7, 8, 9. And then if it's at 270, sine is -1, so 5 minus 4 is 1. Okay. So then the outside part kind of looks like this. Goes up, back over there. So something like that. Okay. Alrighty, there we go. We got our graph again. And let's see, now we got to find the area between the polar curves. The area at the top with the most positive y, okay, between the curves. So I'm thinking that it means like this boundary here, I'll do it in purple. It's like from here all the way over around here to here. But then if it's between it, it means it's like not in common. So outside of this circle here. So like this like area that's in purple. That's what we're looking for, I think. Okay. All right, so let's see. How will we put something like that together? Well, I see that there's some intersection points, and in the previous problem, I solved for them. I'll solve for them again really quickly. The intersection points happen when you set the equations equal to each other. So 5 plus 4 times the sine of theta equals 3. So 4 sine theta equals -2. That means that sine of theta is equal to -1/2. And that'll happen when sine is equal to let's see, 7 pi over 6 and 11 pi over 6. And then for some negative angle measurements, negative pi over 6 and negative 5 pi over 6. And some other ones. You can find more coterminal angles, but I think that's good enough right there. Okay, so let's see here. The way that we would find this area is by doing the following. So like notice, obviously, when you find the area in a polar region, it's adding up all the radii. So like if I'm just focusing on these intersection points right here and here, right? Like if I found those intersection points, I'd have the radius, radii from that starting point. And let's use the outside graph as an example. So this is like the graph of 5 plus 4 sine of theta. Okay, I would like add up all of the radii from the origin out to there. So like all these little like regions, okay, these little triangular regions, I'd add all of them together, and that would give me my integral, the area of the polar region. And I just, as I'm rotating, I'm adding up all the different radii, of course, till I get to like maybe that part right there, okay? So imagine that I'm adding up all of this like red area here. That's not quite what I'm interested in, right? Because I don't care about like all this inside stuff here. I just want the stuff like in here, like these regions, right? So the way that I could do that is by taking all these red radii, and then over the exact same boundary, I could subtract away the green radii that I get from using the circle here, that equation where r is equal to 3. So if I just subtract all of these radii away, and these boundaries inside of it, that should give me my desired region that I want, just that lone purple region. Okay. So yeah, I think that this is going to work. I just got to subtract the two integrals. So I kind of like understand the algebra behind it already. I've got to, define the total area. I'm going to take the red area, which is going to depend on just solely the cardioid. So 1/2 5 plus 4 times the sine of theta d theta. And then I'm going to subtract away. I'm going to take away, that inner boundary, which is the green area. Okay, and the green area is only based off of that circle with a radius equal to 3. So I'd subtract away 1/2 of 3 squared d theta. But I just got to find, make sure that the boundaries work out. I have to have one continuous interval by which I'm going to define the integrals that I have. Okay, so if you're paying attention to the way that the graph was drawn out, like when you graph it out on your calculator, when you hit 0 degrees, right here's 0 degrees right here, the positive x direction, the graph starts right here. And for the green one, it starts right here. That's no good. I want to start like down here, for one continuous rotation. So that clues me in on the fact that I probably actually have to use negative pi6 in this case. Because, if this is 0 degrees or 0 radians, if you rotate downwards in this direction, it's going negative or clockwise. So that would put you at a negative value, and I'm pretty sure that's going to be a negative pi6. Then, so if I start at negative pi6 and then I start rotating this way, right? Like I go through pi, through 0 degrees and then through pi halves or 90 degrees. And then I go all the way through pi or, 180 degrees, all the way until I get to this intersection point. So I think that intersection point is going to be the first positive one that I had, 7 pi 6. I'll bet you anything that that's where it is, if I graph it out this way. So I'm pretty confident that that's what my boundaries are going to be for these two, negative pi 6 and 7 pi 6. And then you can use your graphing calculator to verify that that's what you're going to get. But ultimately, what I should see is just that top part if I verify using my calculator. So just like all this stuff down here would be like all gone, okay? Just the part that I want that gives me the purple region. Okay, so let's see if that's the case. So when we graph it out, that's from a previous problem. Okay, so there's our two equations, 5 plus 4 sine theta, and then r equals 3. Then we go to our window, and let's use the boundaries that we've established. So negative pi over 6 and 7 pi over 6. Oops, not times 6, darn it. Divide by 6, there we go. Then I graph it out. And yeah, sure enough, that gave me the top part. I didn't have the circle drawn for some reason. Oh, I turned it off. Okay, let's try it again. There we go. So yep, that gives us exactly the region that we're after. And if we subtract the two of them, then that'll give us the difference in the area, or just the purple region that we want. Okay, there you go. So there's the graph for number 19, and there's the area for it right here. That'll give you full credit. All right. One more for this one. Yeah, because let's keep the area of videos separate from the arc length. How many more do we have? 22. Oh, it's just 2 problems. Okay. Yeah, I think the next one will be a short video then. All right, so let's see the area between the polar curves and below the x-axis. Okay, so it's a little bit more specific. R is equal to 4 cosine theta and 8 cosine theta. All right, so let's graph it out. So 4 cosine theta and 8 cosine theta. All right, and then zoom 6. All right, there's the first circle and the second circle. Okay, so here's how they look. This gives you a circle starting at the origin, or not at the origin actually. It starts at 0 degrees. So if I plug in 0, that'll just give me cosine of 0, which is 1, so 4. So 1, 2, 3, 4. And then at 90 degrees, cosine is 0. So that'd be 0 times 4, which is 0. So like it goes like this. It goes up and then back over. So it's a circle with a radius of 2. There we go. And then this one is going to be a radius of 4. And it goes all the way up to 8. So 4, 5, 6, 7, 8. 1, 2, 3, 4. 3, 4. There we go. All right, 0 degrees, 90 degrees, and then back to 180. There we go. Okay, so those are 2 circles. That's a little bit better, but there you go. Okay. So the area between the polar curve and below the x-axis, what I'm interested in is this area right here. So between the 2 curves would be like outside of this one and inside of the outside one. So like these 2. And then below the x-axis is this stuff. So it's just this interval, or this area right here. All right. So, with polar equations, remember that I'm like interested in like adding up all the radii. So it looks like it's going to be one of those cases where, if I start, like if I just look at the outside circle, this one, I'd be adding up all the radii, starting at some measurement and going, clockwise or counterclockwise, it doesn't matter. I'm just adding up all the radii for this, okay? So if I add up all these little sections here, it ultimately is going to give me this red area using the outside equation. So I think that what I'm going to have to do is take the outside one, and just like the previous problem, I'm going to have to subtract away the radii from this inside thing. Okay, so like the inside circle. Okay, so this is going to be one of those integral problems like in the area where I need to subtract. So I'm going to take area of the outside one, which is going to be this one. Let's maybe color code it also. It's the red circle. So 1/2 of 8 times the cosine of theta, quantity squared d theta. And then I'm going to be subtracting away the inside circle radii. So that's going to be the green one. So I'm going to subtract away 1/2 4 times the cosine of theta squared d theta. All right, I just got to make sure the boundaries are good on this. So looks like, okay, so if this is, 0 degrees or 0 radians, right, because it follows at like 0 angle measurement, 0 is like the positive x direction, so 0. It looks like they'll intersect each other back at the origin. So this might be one of those cases where it's helpful to set them equal to 0 and solve, okay? It also happens to be where they intersect. So you can find this 2 different ways. You could also just see like, what happens when you set them equal to each other. Either way, you're going to be solving for 0. I'll show you what I'm talking about. Like let's say that I consider that an intersection point. So I'd want to solve for my angle measurements by setting them equal. So, I'd do that. 4 times the cosine of theta is equal to 8 times the cosine of theta. Subtracting 4 cosine theta from both sides, I get 0 equals 4 cosine of theta. And then dividing by 4, I get 0 is equal to cosine of theta. And, this tells me that I need to find any place where cosine is equal to 0. So for theta, that would be pi halves, 3 pi halves. And then for negative angle measurements, that would be negative pi halves, negative 3 pi halves. And you can do more coterminal angles if you want. I just like to get a couple positive ones, a couple negative ones. That usually does the job. Ultimately, but on the other hand, if you notice that it's just past the origin, so you're like, oh, I just want to look at the origin points. Well, guess what? 4 cosine theta equals 0. Divide by 4, you still get cosine theta equals 0, which is like, the same thing that we had over here. Same thing with this one. If you use 8 cosine theta, divide both sides by 8, 0 equals cosine of theta. And again, you're like at the same spot, here again. So you still end up with these same angle measurements regardless. So how do we just get to this point? Well, there's actually a couple different ways that you can do this. All right, I'm going to start by just using probably just negative pi halves again. Because again, if this is 0 degrees, I'm just going to go back this way. So if I'm going clockwise, that means I'm going in the negative direction. So I think that to get back over to that spot where they're in common, I would just use my very first negative angle measurement, so negative pi halves. And then that's cool, because if this is the starting point for negative pi halves, right, then as I rotate counterclockwise, okay, I would just have to go over to 0 degrees to get, the lower half. So that's what I'm going to try to do. I'm just going to put negative pi over 2 here and 0. And again, if I use my calculator, I bet that it's just going to be the lower half of each of those, graphs. That's what I want. I just want the lower halves. And let's verify that that's the case now. So if I go to my window and then go from negative pi over 2 all the way over to 0, yeah, and check it out. It's just the lower half. So this is all I needed to do. Just subtract the two areas. Take the red one, which is the larger area, subtract away the green one, and that'll give me the area of the purple region that I started with. Just the lower half between the two of them. So this one. Okay. All right, so there you go. There's number 19 and number 20. There's a bunch of different ways to do these because, it doesn't, as long as you get that shape that you need, the boundaries can be different and stuff like that, but it gets you the area. Okay, well, I hope you found this helpful. If not, go find your calc teacher, work with them one-on-one, or just get some help from friends or something. Yeah, I'm Mr. Cook. If you need some help from me, find me in the morning or after school. I'm always here to help out. Just track me down and I'll help you out. Okay, well, thank you very much for watching this one. We got one more left, and that's going to be on arc length. I'll see you in the next video. Bye-bye.